Disruptive Technologies and Geosciences. I'm going to talk on the ground and into the cloud. It's really been a fun project for me. It really gave me a chance to look back and see where we are now and what the future may bring. Officially, my degree is in carbonate sedimentology and geochemistry, and I guess if you really need some sleep aids, reading my dissertation on Mississippi Valley lead zinc deposits might help you. I started out teaching geology and oceanography, but soon was captured by geographic information systems and remote sensing, and have been focusing on using those technologies. First, I want to talk about what is disruptive versus evolutionary technology. You know, disruptive, the old is gone, and there's something new that becomes the norm. And one example of this is the telegraph to the telephone. You know, Harvard Business School professor Clayton Christensen coined the term, and really he said the new technology may not even be very interesting to people. You have to market it, and actually people couldn't believe they would want one of those telephone devices in their homes. Evolutionary, though, is more incremental change, and generally you don't have to market it. It just kind of evolves into it. I think landline phones to cell phones are one of those evolutionary technologies we can all see that, you know, I can see a time when we may not have landlines except in very few cases. Disruptive, really what I'm going to be using though is kind of a mix of those two, both the totally innovative to the incremental. And I also want to stress that they're still basics and they still provide the skills that allow you to really understand and use those disruptive technological innovations. Now this slide is it's a paragraph based on a National Science Foundation study that suggests what future geoscientists are going to need to know and be able to do. It's a current study. Industry has put in their input into what we think should be known by future geoscientists. One of them, and I'm going to highlight these because you can't read that paragraph, is effective two-way communication, both with geoscientists and with non-scientists. And I think this is really important. I think geosciences suffers because we don't speak well to non-geoscientists. I love our geology maps, but for non-geoscientists, often they just look like modern art. They really can't get information. So if you're going to be working with both scientists and non-scientists, learn how to communicate in both directions. Another one is strong computational skills and the ability to manage and analyze large data sets. This is becoming more the norm. We get huge data sets. Terabyte is not even unknown anymore. And you need to know how to use your computer science skills, your mathematical skills, and yes, calculus still counts, but you need to know how to really build those data sets and manage them. Another one is it suggests you have to have good, strong field skills. So field camp is very important. And a working knowledge of GIS is mentioned by industry. Graduates also should be prepared to experiment with new and evolving technologies. So that means that those disruptive technologies that may or may not become the norm in the future, you should take a look at them, evaluate them for what you're doing, and then use them if they're effective. Well, building those essential skills, the field camp, I went out to about 20 different university programs and looked at what they said they wanted students to know in field camp and what they wanted them to bring. And you know, it's really interesting. I don't think that has changed in the last 75, maybe 100 years. So map boards, buttons, field notebooks, all those things. And it was kind of fun because I started thinking about it, and I still have most of my things. I couldn't find my Mohs hardness scale or my color chart, but here's some of the things that I took to field camp with me. Two of the mineral specimens on the left we can talk about later. You know, nice to have things for the field camp. Of course, as camera was film, now with electrons you take pictures. Binoculars, we used to have a thing against radar mapping, but I think they are very useful. But where is the technology? I didn't really see much unless you want to count a Brutton as technological. Well, it will come, but really first learn how to go out in the field, look at the rocks, walk on top of those rocks, identify the rock types, the structures, and other things you see, the relationships, and learn how to document them. So keep your field notebook, build those strat columns, and of course, make a paper map. Well, evolving technology, there's so many new things coming on for field camp. We'll be using GPS or some form of digital locational device. Tablets are becoming ruggedized. You can take them out in the field, and most of the things on here you will be using as a professional. My phone now has more tools on it than I could have afforded to buy when I went to field camp. And of course there's satellite phones and cell phones, and we have a spot transponder. You may be in a place where there isn't a cell phone connection, and it's a good thing to have in emergencies. And of course then you need some way to power all that electronic equipment, and that can be as simple as your car and a USB port, or it may be a solar or other generator. And there are many advanced tools that you may be using as a professional. So the other thing I want to talk a little bit about is the enabling technologies that are disruptive and evolutionary. And here it's the industry term, is it better, faster, cheaper? Well, computers and software, yep, they have come a long way, and they are very useful, and the software is much more powerful, and you can do many more things visually. Also, really, that's been enabling and transformative is the internet and the web. Speed, accessibility, availability of data, storing your data, managing your data, data portals, and then knowledge sharing. Doing YouTube videos or other videos where you can tell people what you've done and how you've done it and help them learn how to do it. Disruptive technology online. When I asked people in the know what they felt was the most disruptive thing, you know what they said? Google Earth. Google Earth really didn't come on the scene until about 2006 and didn't become really well known immediately. But it does allow us to create a view of the Earth, go into our region that we're studying, and it's free, it's pretty simple to use, and it gives us a pretty picture of what that looks like. Of course, when it first came out, it looked like a patchwork quilt because they zipped together images from different times of the year, but it's getting better and better. YouTube is also another thing that they said has been disruptive, and I mentioned that before, just-in-time learning and sharing what you do and how you do it and learning how to do something new. I dumped a glass of water into my laptop and I was ready to just throw it away. Well, guess what? Went to YouTube, found about water in your laptop keyboard, found out where to buy my new keyboard, how to install it, and now my laptop works fine. So it's another thing that you can use. And of course, if somebody asks me something, and I will first ask them, have you Googled it? Yeah, there's a lot of junk out on the internet, but there's also a lot of good stuff. So whether you're using Wikipedia or just general resources, learn how to use it. And you shuffle through the good stuff and the not so good stuff, and document it. Also, there's a lot of good images out there. Just be careful that you do have the right to use them. Portals, I mentioned, so many portals now that allow you to download data, and they can tell you how they collected the data. Find out, is it up to date? How is it done? So make sure you get the metadata too. Here are just two examples of Google Earth and ArcGIS Earth. And the other thing, when it first came out, you tried to lay your vector data on it, and it didn't. There were issues with datums and projections. But more and more you can actually look at things in 3D. So I want to talk to some people about this particular landslide out in the Parsimero Valley. New technologies allow us to visualize, model, and share what can't be seen easily. And this is really important. So whether you're looking at hydrologic processes and fluid flows below the surface, or mineralizations, or wells, or mining, there are just many ways now that you can visualize that in 2D, 3D, and in 4D time lapse. Web portals allow us to look at things things, whether it's coastal processes or earthquakes, getting really good data for base maps. You know, many new laboratory tools let us look at the very small, and I'm not going to really talk about those very much. What I'm going to do is talk about those that allow us to view and analyze data from the very large, okay? And this is remote sensing. USGS has a nice short definition of what is remote sensing. So it's acquiring information about a natural feature or phenomenon, such as the Earth's surface, without actually being in contact with it. And you can see pictures here. I start with a ground-based sensor that could be collecting air quality or other things, to radio telescopes. More and more are we seeing data coming from very deep space. Big thing on the horizon is the use of drones, and whether it's fixed wing or quadricopters or other things, that is going to be very big for everyone. We've had aircraft for a long time, but the difference with drones is the cost and the usability, and new FAA rules are allowing more of us to do it. So whether it's aircraft or drones. Also satellites, and I'm going to talk a lot about some of the satellite options we have. Major thing I want to stress is these aren't just pretty pictures. So when I look at Google Earth, I'm getting a pretty picture, and I'm getting a lot of good information from that. But for remote sensing, I can get more information from each of those images, and I can look at things like landslides, mineral deposits, Earth studies in various ways, and much, much more. There are really two types of remote sensing. One is called active and one is called passive. Now, for active, the energy source has to be supplied by the sensor. And that's where we come in with Lidar, which is a pulsed laser beam, or SAR, or INSAR, which is a radio waves, either singly or in parallel. Passive, on the other hand, the sensor just collects the energy that is being generated from the solar electromagnetic spectrum. Those include MODIS, Sentinels, lots of commercial high-resolution imagery, and just lots of different data sources. So there are 4 remote sensing imagery resolutions I want to really stress. One is spectral. So what wavelengths of the electromagnetic spectrum does that particular sensor or sensor platform collect? The next one is spatial. That's the size of the area or the footprint of the image itself, and the size of each of the pixels or cells where the data is being collected. Temporal, is it a one-shot time that this image will be collected, or is it going to be able to be collected from data from the past, or weekly, monthly, yearly? So it's the temporal, the time that location is being observed. Radiometric's a little harder to understand, but it's the sensitivity of the sensor. For a long time we had, Landsat had the possibility of sensing 256 different grayscale values. Now Landsat 8 is up to 55,000 or so. So the more sensitive the sensor is, the more information you can gain from a remote sensed image. You've probably all seen a graph of the electromagnetic spectrum, and this is one of them I want to talk about. Looking at the different frequencies, radio waves all the way up to gamma rays, and just want to stress that what we do with our eyes, we see in a very narrow band of the electromagnetic spectrum. Well, if I take this same graph and sort of stand it on end, this graphic shows the approximate, I want to stress approximate, values of different types of imagery, what parts of the electromagnetic spectrum they use, or how their data is transmitted. So multispectral comes in at around 450 to 2300 nanometers. Lidar, you can see, as in comparison, is about 250 to 2000 nanometers. INSAR or radar is approximately 1 to 1,000 millimeters. So notice the difference change in frequency. And then I've got the ALMA radio telescope, which is looking at pretty long wave radiation, 1 millimeter to 250 millimeters. Lidar, and there's a really good tutorial out on NOAA's site on Lidar, is an active remote sensor. So it's sending out a radio beam, a laser beam, and it's emitted, and then its return signal when it has contacted something is collected. This provides data and a data cloud which can be resolved into regions of the first to the last returns, giving extremely good resolution but very large data sets. And you can see on the graphic here the data cloud that's being generated and the different return parameters. One of the things as a geologist, I always wanted to go out and remove all that green stuff. You know, the forestry likes those trees, but geologists, I'd just assume they weren't there. Well, with LiDAR, we can do this now. On the left-hand side, images A is an aerial image. B, you can see the fairly low resolution topo map of that region. And C is the much pretty low resolution digital elevation model. But D is the LiDAR data. So I can really see a lot in the image, but it allows me to look at the last return and take away those trees. So I can see structures, I can see landslides, I can see all sorts of things that I couldn't have seen before. And the digital elevation model can be very high resolution. I can even put back the trees if I really want to. LiDAR, laser scanning, and INSAR also allows us, with our huge data sets, to really get down to very minute millimeter resolutions. And this can be ground, drones, aircraft, different ways to actually collect this very high resolution data. For passive, solar energy and sensors to detect that information about features. Well, our human eye is really a passive remote sensor. We are actually, the sun is illuminating an object, the energy from that object is being reflected, and the sensors in our eyes collect that information. Our brain is the computer processor, and it creates the image that we see. Satellites and geologic structures can be seen in much greater detail and color-coded in various ways that really allow us to see them as we've never seen them before. So much wider use of the electromagnetic spectrum than just our eyes. This is just an example of looking at provinces and different types of geologic structures. MODIS is a 36-band satellite image that is very low to very low resolution, so 1 kilometer sized pixels. But it does have very high temporal. It's every 2 days it's collected. And this happened to be collected on the day that we had the big fire in Stanley and also in Yellowstone. And you can see the smoke from it. It's it's the meteorological thing that we're usually viewing. Another one is Aster. It's got 14 bands that it uses, and it's got pretty good resolution, 15 to 90 meter resolutions. But unlike MODIS, it's not collected every 2 days. It's collected only 8 minutes per pass, and it can be focused on various areas. So this happens to be Morenci copper mine, but it is pretty interesting geologically, and of course it doesn't have good repeat. Discover, space weather and drilling. This is an instrument, a satellite instrument that has sensors on it that collect the plasma velocity, density, and temperature of the solar wind. It also collects the strength of the using a magnetometer, and the direction of the solar wind. And it's being used by industry now to guide subsurface drilling And it also can allow us to know if there's going to be an geomagnetic storm. So we'll get warnings of bad space weather that can really affect our electronic grid. Why am I going to focus on Landsat? Well, I'm going to talk a lot about Landsat because it's low cost. It's pretty easy access. You have to know a few things, but there are tutorials out there. It does have good continuity, so you can go back to, theoretically anyway, to 1972 and look at images. And it is pretty current. It can be within days or weeks of when you need to see the data. One thing is it uses the same basic principles as others do, so it's easy to learn using this data. So that solar energy can be absorbed, transmitted, scattered, or absorbed by objects and readmitted. And I want to stress here is look at the top of the atmosphere. So this energy has had to come through the incoming to meet the feature, and then it is reemitted and collected at the top of the atmosphere. It is usually collected if it's in line of sight of a collector, or it can be stored and then transmitted when it's over one of the satellites. And it is then transmitted to the ground where it is cleaned up and then processed and put out on the internet for downloading. So this is a graph that I think is a bit confusing. The y-axis is the percent transmission through that atmosphere. Okay, I was talking about incoming and return. And then the x-axis is the wavelength of energy that is able to make that. If I look at this, the gray regions are specific windows where the wavelengths can penetrate through the atmosphere and be recollected. So that's the gray shading. And you can see I have Landsat 7 here, and Landsat 8. These are the regions that those two satellites collect and have sensors that collect data. Interesting thing too is you can see what limited area I see, so you can see that it collects in many more regions that we cannot see. But also I want you to note that the numbering of those bands, whether it's Landsat 7 or Landsat 8, are not the same. And that's going to be true with whatever data you may be using. You have to know what bands are being collected and what regions of the electromagnetic spectrum they represent. This is just a little chart showing the difference between Lidar, Aster, and Landsat 7, so the different wavelengths. So what does it really look like when you get this data? Well, this is a sandwich of all the different data layers for Landsat 7, and I have 8 bands, and it shows the grayscale. So each of the pixels have a brightness value that is given to it. It also corresponds to a number that tells the computer how bright to make that object. So here's what one band looks like in grayscale, and this happens to be San Fernando Valley, California. When you download it, this is what you're going to see. Now, initially, you'll just have one folder. It'll be a tar folder, and it'll tell you what sensor it is. You have to unzip it twice in order to find the band data. And each of these different band data are a different layer of data. So you get, with this, bands 1 through 7, and then you have your metadata. So be sure and keep both the data and the metadata. If I go in and look at it in finer detail, this happens to be one band, band 7. It's the brightness and its digital numbers for Landsat 8. So if I zoom in further, I can see a rectangular area. I can begin to identify it. Looks like a building, right? And if I zoom in really well, I can see that each of those pixels, which represent a 30 by 30 meter square of the Earth's surface, I can then use identify and find out what exactly the number is that corresponds to that level of brightness. So each of the pixels will have a value that is numeric and then is generated in a grayscale that we see. I can take then all of the bands, remember we have more than one band for these satellites, and take all the values for each of the pixels and graph them. So here I have the wavelength and its brightness, and I can graph it and I can identify what it is. Now this is from the National Mineral Reference Collection in Canada, showing the mineral Kodame clay. I can take it, though, I can look at all the different pixels, and I can graph those things that I think is soil, water, whatever, and identify what that feature really is by looking at its signature graph in a wavelength versus reflectance. Well, the other interesting thing that I could do is, in a computer, we use 3 color guns to make an image. So I can take any 3 bands and tell the computer to combine them and color them. So here you may take band 1, 2, and band 3 and tell it band 1 I want it blue, band 2 I want it green, band 3 I want it red, and it will combine it and show you what that image looks like. Now this is natural color on the left, on the right from Landsat 7. So it's bands 3, 2, 1, and looks pretty much like what we think our eyes would see looking down from above. Sometimes that doesn't give us very much information, so I can take other bands, and here the middle one is called a false color image, and it's bands 5, 4, and 3. And actually the greens in this image are red. The urban structures are light blue to darker blue, so I can find out more things about it. The last one is another band, pseudo color or false color, band 753. When I have a remote sensed image, especially from a place I'm not familiar with, or I want to look at geologic processes, I want to look at patterns from the image in different composites. I can use those spectral signatures to try to identify certain things and cluster them or group them together. And to group them together, I can use software functions called supervised or unsupervised classification that can help me identify features in an image. So with supervised, I tell the computer, let's look at this pixel. It's water. I want every one the other pixels that have the same values to be clumped together as water. I create a file with the different features I want to identify and tell the computer, okay, use this file and clump them. Or I can unsupervise it. I just tell it, put all the like values together in clumps, and I'll review it and unclump them and regroup them. So that's 2 ways to do it. Once you've done your imagery and you've done your analysis and you need to present it, again, I want to stress, know your audience. If they're geologists, you can use one type of geology format for presentations. If they're not geoscientists, what do you want to stress about it? And you also need to know what format you're going to do it. Is it going to be a paper? Is it going to be in a poster session? Is it going to be interactive on the web? So I would stress that you take a cartography class, you learn about projections and datums and colors and scales and different ways to present your information. So some of the factors you need to consider when you use remote sensing data on geoscience problems. Scale or resolution. Where is the study location? How large is that area? What is the size of the features under study? And is this a one-time event or multiple times events? So if whatever you're going to view is smaller than the smallest pixel size, you're not going to see it. So if you need it over time, you're going to have different resolutions, all different things you have to think about. Also think about data and its cost. Is it free? Can you get access to it? Or is it really very costly? And do you have the hardware, computer programs, other analysis techniques, and your own skill set to do that kind of a study? The last thing is, why is a study important? And in science, we can do many, many studies that we find interesting, advance the state of the art, all sorts of things. But in business, they're going to look at return on investment. It's ROI. So I want to mention some disruptive economics. Just because we find it interesting and really wonderful doesn't mean that industry is going to want to do it. So they are interested back to that better, faster, cheaper. Also, economic climates change, and when it is, robust geoscience time, they will fund things that they won't fund when times are tougher. So the other thing you need to be aware of is the industry may find it very interesting, but they may not mention it because it really does give them an advantage. So it may be proprietary or restricted, but I think your studies, just remember to create your own portfolio, both hard copy and digital, and keep it, because that's going to be your history, and it's how do you show your work when you go to an interview. Well, one of the problems I think you see now is there are so many satellites and so many ways to look at things, and that is a problem. In fact, one of the biggest problems I think today is there's too much information, there's too much data, there's too many satellites, there's too many websites. So you are going to have to really learn how to limit what you use, what you learn, and what you're going to spend time on. You can go out and find data, talk to other people, find what industry is using, do your research, and find the best. Now this is an app from Esri that just came out, and it does all of these composite images. And it's really quite neat. I mean, you can look at an area, you can look at it over time. Here it happens to be the Rexburg area in the wintertime and the snow. So it's really quite interesting. And you can look at it over changes over different times of the year, just all sorts of things. The only thing about it that kind of bothers me is it's button pushing. So what I really suggest you do is learn the basic skills in your field camp, learn how to collect, integrate, manage large data sets, and use different software for multiple data sources. And look at the technology and use what's useful to you, but don't get lost in it. And be a problem solver, not a button pusher. While I think that site from Esri is really good, very interesting, very informative, know what happens when you push the different buttons on that website, and learn how to effectively visualize your results. And of course, again, keep that portfolio. I want to just mention one good site that I found that Mark worked on too. It's a YouTube site. I Get Remote Sensing Education Channel. There are 22 videos out there that talk about various concepts for remote sensing. I hope there's questions, and this is my contact information. I work on 2 different National Science Foundation grants, and that is my email address. Thank you very much.